Please take a look at Theorem 2. Suppose a and b are positive integers. Then the greatest common divisor of a and b is Sna plus Tnb, where Sn and Tn are nth terms of the following sequence defined recursively. Recursively means we start with two initial values. S0 is 1, S1 is 0, T0 is 0, T1 is 1. Here is what we do next. Sj is equal to Sj minus 2 minus Qj minus 1, Sj minus 1. Tj is equal to Tj minus 2 minus Qj minus 1, Tj minus 1. What are these Q's? These Q's are quotients in the divisions of the Euclidean algorithm when it is used to find the greatest common divisor of A and B. Here is what we mean by that. Please take a look at this. Note that here J is running from 2 to n. So if J is equal to 2, Q subscript J minus 1 is Q1. This Q1. If J is equal to 3, Q subscript J minus 1 is Q2. This Q2. And so on. If J is equal to n, this is Q n minus 1. This. Let us compare Theorem 2 with Bezout theorem. Bezout theorem tells us that it is possible to find integer numbers m and n such that the greatest common divisor is ma plus nb. To the contrast, Theorem 2 gives us explicit formulas for m and n. M, according to what is written here, is Sn. N is equal to Tn, where we find Sn and Tn using these two formulas, where the initial terms are 1, 0 for S0 and S1, and 0, 1 for T0 and T1. Now let us prove Theorem 2. In order to prove Theorem 2, we will prove the following. Rj is equal to Sja plus Tjb. Note that indeed this implies this. Here is why. Let us go back to the Euclidean algorithm. According to the Euclidean algorithm, Theorem 1, the greatest common divisor of A and B is equal to Rn. So, in Theorem 2, if we replace the greatest common divisor of A and B by Rn, we'll get the following. Rn is equal to Sna plus Tnb. Note that this immediately follows from here if J is equal to n. In other words, if we prove this, what is written here will follow immediately as a particular case when j is equal to n. So here we prove even a stronger result. What is written here is a generalization of this, because this follows from this when j is equal to n, thanks to the fact that the greatest common divisor of A and B is equal to Rn. Next, how do we prove this? We will prove it by induction. Step 1. For j is equal to 0, this is true, since R0, if j is equal to 0, the left-hand side becomes R0. R0 is equal to A. Guys, R0 is equal to A thanks to this. Remember, in Theorem 1, we put R0 is equal to A. So, R0 is equal to A by Theorem 1. Note that A can be rewritten as 1 times A, which is A, plus 0 times B, which is 0. Lastly, note that 1, according to what is written here, is equal to S0. We leave A without change. 0, according to what is written here, is equal to T0. We put here T0 and we leave B without change. Now let us put pieces together. R0 is equal to this, which proves this formula for j is equal to 0. Similarly, if j is equal to 1, the left-hand side becomes R1. But by Theorem 1, R1 is equal to B. So we replace R1 by B. Next, B is equal to 0 times A, which is 0, plus 1 times B, which is B. 0 plus B is equal to B. Lastly, 0, according to what is written here, is equal to S1. So we replace 0 by S1. 1, according to what is written here, is equal to T1. So we replace 1 by T1. Conclusion, R1 is equal to this, which proves this formula for j is equal to 1. Next, step 2. Since in step 1, we show that this is true for both j is equal to 0 and j is equal to 1, we can safely suppose in step 2 that this is true for some j is equal to k minus 2 and j is equal to k minus 1, where k is greater or equal to 2. That is, suppose this and this. Once again, we can safely suppose that this is true for some j is equal to k minus 2 and j is equal to k minus 1, where k is greater or equal to 2, because indeed, for example, for k is equal to 2, this is true and this is true, thanks to this and this. Now, step 3. In step 2, we suppose that this is true for j is equal to k minus 2 and k minus 1. Therefore, in step 3, we prove that this is true for j is equal to k. We want to prove this. Over here, we put question mark. In order to prove this, let us go back to the Euclidean algorithm, to Theorem 1. Please take a look at this formula over here. Note that this is a copy of this. So, indeed, by the Euclidean algorithm, this is equal to this. Next step. Let us move this term to the left and switch positions. If we move this to the left and switch positions, on the left we will get RK. It's exactly what is written here. On the right, we will get this minus this. It's exactly what is written here. By step 2, RK minus 2, which is over here, is equal to this. We put this expression here. Again, by step 2, RK minus 1, which is over here, is equal to this. We replace RK minus 1 by this expression. Done. Next, we expand parentheses. Here we expand parentheses for free, means nothing changes, because the sign in front of parentheses is plus. Here, when we expand parentheses, this plus becomes minus, because in front of these parentheses we have minus. And of course, sk minus 1 times a times this is over here, tk minus 1 times b times qk minus 1 is over here. Next, let us switch positions of two terms. Let us move this term over here and this term over here. After that, over here, a is a common term. Factor it out. Over here, b is a common term. Factor it out. Lastly, according to what is written here, if we apply these two formulas with j is equal to k, sk is equal to this. For convenience, let us compare. Please take a look at this. Here are the formulas. Indeed, if j is equal to k, right-hand side is sk minus 2 minus qk minus 1 times sk minus 1, which is exactly what is written here. Of course, if we switch positions of this and this. Similarly, if over here we replace j by k, the left-hand side becomes tk, the right-hand side becomes what is written here, again, if we switch positions of q and t. So, rk is equal to ska plus tkb, which is exactly what we wanted to prove. Talking about applications. One application of Theorem 2 is already discussed. Please compare once again Theorem 2 and Bezout theorem. Bezout theorem says that there exist integer numbers m and n such that the greatest common divisor is ma plus nb. Bezout theorem does not give us an algorithm of finding m and n. This theorem Theorem 2 tells us how to find m and n. Please take a look at this example. Note that over here we use same numbers as in example number 1. Same numbers. We know how to find the greatest common divisor of these two numbers. Over here, the greatest common divisor is 18. But now let us come up with this result in a little bit different way. Please take a look at this table. This table consists of 1, 2, 3, 4, 5, 6, 7 columns. In column number 1, we start from 0, 0, 1, 2, 3, 4, and so on. Column number 2 are values of Rj. Now, if j is equal to 0, this is R0. And remember what is R0. R0 is A. In our case, A is 252, so we put here 252. Column number 3 are values of Rj plus 1. If j is equal to 0, this is R1. And R1 is B. In our case, B is 198. We put here 198. Next, column number 4 are values of Qj plus 1. If j is equal to 0, Qj plus 1 is Q1. And by the Euclidean algorithm, Q1 is 1. We put here 1. Lastly, if j is equal to 0, Rj plus 2 is R2. According to what is written here, R2 is 54. We put here 54. So, please take a look once again at these 5 numbers. We always put here 0. In order to come up with these numbers, you just copy the given numbers A and B. Done. In order to find these numbers, we use the division algorithm. We divide this by this, find the quotient, and find the remainder. The last two numbers are S0 and T0. As we discussed, S0 is 1, T0 is 0. We put here 1 and 0. And by the way, now let me switch to row number 2. If j is equal to 1, S1 is 0, S2 is 1, according to what is written here. Next. So we know how to come up with all these numbers in row number 1. We know how to come up with these numbers in row number 2. In order to come up with these numbers, we copy this over here, this over here, and then apply the division algorithm in order to find quotient and remainder. Note that these two numbers come from row number 2 here. Over here, 336. We put here 336. Next, row number 3 starts from 2. We copy this number over here, this number over here. Then we divide 54 by 36 using the division algorithm. Quotient is 1, remainder is 18. It's exactly what is written here. But now, all of a sudden, over here we put 1, over here we put -1. Folks, any ideas? How do we come up with this and with this?
From formula?
We use the formula. We use these two formulas. According to these two formulas, Sj, in our case S2, is equal to Sj minus 2. If j is equal to 2, this term is S0, and S0 is 1. Minus Q1, once again, if j is equal to 2, this is Q1. And Q1, according to what is written here, is 1 times S1. And S1, according to what is written here, is 0. In short, this number is equal to this number minus this times this. Repeat once again, shortcut. This number is equal to this number minus this times this. This is equal to this minus this times this, which is indeed 1. Similarly, according to this formula, this number is equal to this minus this times this, which is -1. Keep going. In order to come up with this number, we just copy this. In order to come up with this number, we copy this. When we divide 36 by 18, quotient is 2, a remainder is 0. And as before, in order to come up with -3, we subtract from 0 3 times 1. Same pattern. Remember, 1 is 1 minus 1 times 0. -3 is 0 minus 3 times 1. Similarly, 4 is 1 minus 3 times -1. Very last step. Since here we have 0, we need only the very last row. In order to come up with these numbers, we subtract from 1 times -3. 1 minus -3 is 4. -1 minus 4 is -5. And now, this number is the greatest common divisor it's over here. But this table gives us additional information. Please take a look at these two numbers. It turns out that 18 is equal to 4, which is over here, times 252 minus 5 times 198. Conclusion: if the only goal is to find the greatest common divisor, we apply the Euclidean algorithm. However, if we want to write the greatest common divisor as a linear combination of these two numbers, we apply this approach. M is 4, which is here, N is -5. So if we only need the greatest common divisor, either you use this approach or you use this table without the last two columns. However, if in addition we want to write the greatest common divisor as an integer linear combination of these two numbers, we need columns 6 and 7.
So the linear combination is unique?
No, it's not unique. That's the whole point. Please take a look at this. One can show that 18 can be written as a linear combination of these two numbers in infinitely many ways. And by the way, one can also show that this is a complete description of solutions of the following equation. 18 is equal to m times 252 plus n times 198. We will discuss these formulas later. All you need right now is a particular solution, not the general solution. Was that your question?
Yes, absolutely.
So now you may ask me a question: is it possible to come up with these numbers without this table? The answer is yes. We can actually use the Euclidean algorithm only. So please take a look. Over here, we copy same thing as before. We copy this over here. Here is what we do next. Please take a look at row number 3. Move this to the left. If we move this to the left and switch positions, on one side we get 18, on the other side we get 54 minus 36 times 1. It's exactly what we have over here. Next step. According to row number 2, 36 is 198 minus 54 times 3. It's exactly what we have here. Here's what we do next. We start from this. Done. Then we replace 36, which is exactly what is written here, by this expression. Done. After that, we expand parentheses. Since we multiply by 1, the only thing that changes is this minus times minus becomes plus. So 54 plus 54 times 3 is 54 times 4 minus 1 times 198. In other words, if we combine this and this, we get the following. 18 is 54 times 4 minus 198 times 1. Keep going. According to row number 1, 54, which is over here, is equal to this minus this. It's exactly what we have over here. Last step. We copy this over here and then replace 54, which is over here, by this expression. Done. And then expand parentheses. 254 times 4 is over here, minus 198 times 4 minus 198 times 1 is 198 times 5. So 18 is equal to a linear combination of 252 and 198. It's exactly what we got over here. So it's up to you to use this table or to apply this approach. My recommendation, if you understand basic principles that are behind these numbers, this table allows us to find m and n faster than this approach. Next, now solution 3. So I give you 3 different ways of finding not only the greatest common divisor, but a solution of the equation 18 is equal to 252m plus 198m. We discussed 2 methods. Now method number 3. Please take a look at the following. Let us consider the following fraction. 252 divided by 198. Step 1. Rewrite this fraction as an integer plus the corresponding proper fraction. Note that this fraction is improper because the top is greater than the bottom. This is a proper fraction because now the top is lesser than the bottom. Next step. By arithmetic, this is equal to 1 divided by 198 over 54. Observe that since this fraction is proper, this fraction is improper. Keep going. Rewrite this as an integer plus the corresponding proper fraction. Flip it again. Apply the same approach. Note that this is 1/2. We stop. After that, we do the following. We replace this fraction by 0 and convert the whole thing into a single fraction. So these two numbers is a solution of our equation again. Folks, any questions here?
How could you tell by this method that the 5 is negative and not the 4?
Very good question. I would recommend the following approach. So, bigger number is this, smaller number is this. Therefore, in order to come up with 18, we multiply 252 by a smaller number, 198 by a bigger number, and then, of course, in between, we have to put minus, because if we put plus, the result will be big. Does this make sense?
Yes.
Folks, any other questions?
Can you repeat again, when do we stop?
Very good question. We stop when this number is divisible by this number. We cancel out the top, we get 1, we stop. And now we have just few more examples. Express 1 as a linear combination of 5 and 8. Since 1 is the greatest common divisor of 5 and 8, we can apply one of the above procedures. For example, let us apply method number 3. 8 over 5 is equal to 1 plus the corresponding proper fraction 3 over 5. We flip. We rewrite 5 over 3 as 1 plus 2/3. We flip. And then 3 over 2 is 1 plus 1/2. Since we got 1 here, we stop. Lastly, we replace this by 0. Done. And then we convert this fraction into a single fraction. So top is 3, bottom is 2. We multiply bigger number by smaller number minus smaller number by bigger number. The result is 1. Similarly, express 1 as a linear combination of 21 and 34. 34 over 21 is 1 plus the corresponding proper fraction. We flip. We rewrite this as 1 plus the corresponding proper fraction, and so on and so forth. We stop when we get 1 on the top. Then we replace 1/2 by 0 and convert this into a single fraction. Lastly, we multiply 21, smaller number, by 13, bigger number, minus we multiply 34, bigger number, by 8, smaller number. Observe that 21 and 34 are consecutive Fibonacci numbers. And this is not a coincidence. One can show that if we apply this procedure to 2 consecutive Fibonacci numbers, over here we will get only ones. Therefore, the number of steps is as big as possible. Moreover, observe that 13 and 8 are also Fibonacci numbers. And indeed, one can show that if we consider the following equation, fnx plus fn plus 1y is equal to 1, where fn and fn plus 1 are Fibonacci numbers, then a solution of this equation is also 2 consecutive Fibonacci numbers. And this happens thanks to the following identity. Please take a look at the following identity, this one. Know that if m is equal to n plus 1, the subscript is 1 and f1 is 1. Conclusion. A solution of the equation fn plus 1 x minus fn y is equal to plus minus 1 is a pair of consecutive Fibonacci numbers.